Okay, dear students, welcome back to our today's lecture. आज की लेक्चर में हम डिस्कस करेंगे about the vibrational energy levels of a diatomic molecule. So, in our last lecture, we have seen we have I can say we have determined the energy equation for a diatomic molecule and how the vibrations change in the vibration or vibrational bond vibration of a diatomic molecule changes the energy of that particular molecule. And when we plot the energy versus our internuclear distance, this x-axis is our internuclear distance, and on y-axis we are taking our energy, that is kilojoule per mole. So when we plot the internuclear distance with respect to the energy of a diatomic molecule, we have seen how the energy of the diatomic molecule changes with changing the position of the atoms. That is, either we are compressing the bond length or we are extending the bond length. So we got this type of parabolic curve for a diatomic molecule, and the energy of this kind of diatomic molecule is given by an equation which is E is equal to half of K R minus R equilibrium square. It means that the energy is depending upon two factors. One is K, that is our force constant, and second is the change in the bond length from our equilibrium position. For example, if this is our REQ, that is the equilibrium position, or I can say the actual bond length of that particular molecule. And if you either compress or stretch this bond, the energy of the molecule is also changing. For example, if we take this as energy level 1 and energy level 2, so either compressing, so this is our equilibrium bond length, or we can say the bond length of the actual molecule. So by either compressing or I can say elongation or elongating or extending the bond length, the overall energy of that particular diatomic molecule is changing. So the zero of, I can say, in this parabola curve. So this curve is a form of a parabola, or we can say that is a parabolic curve. And this model of a vibrating diatomic molecule, also known as simple harmonic oscillator, is excellent. We have already said that this is the excellent starting point for the discussion of a vibrational spectrum of a diatomic molecule. So in this equation, we can say that the zero energy of this diatomic molecule is when your R and R equilibrium is equal. So I can say the zero of the curve is, or I can say the zero energy of the curve E is equal to 0 is when your R is equal to R equilibrium. It means this is the position when your molecule is at their actual bond length. It means when there is no disturbance occurred in this diatomic molecule. So this is the 0 point. So at this point, your diatomic molecule will be, one atom will be exist here and the second atom will be exist here. Then the we can say the energy is 0, because this is the energy axis. It can be 0, 1, 2, 3, 4, 5, and so on. In this way, the energy of this diatomic molecule may increase. So at zero energy, the equation be like, or I can say at zero energy, this R and R equilibrium will be 0. So the equation will be like E is equal to half of KR square. This kind of energy equation we may get at this zero energy, the 8 energy equals to 0. Then if you raise the energy of this atom, this molecule from this 0 to E1 level, then what will happen? Then as you increase the energy of this molecule, energy increase होने से क्या होगा? For example, if I increasing the energy of this molecule from 0 to this E1 level, what will happen here is the oscillation of this molecule will also increase. So I can say, as I increase the energy of the molecule from 0 to E1, what will happen here is that the oscillation will also increase. Oscillation will increase, or I can say oscillation become more and more vigorous. Why vigorous? Why? Then what we mean by this oscillation? Oscillation, increase in oscillation, it is nothing. It means that the degree of your compression or elongation, yeah, extension will be greater. Degree of compression and extension will be greater. It means as I am increasing the energy of this molecule, for example, if this is our HCl molecule, so I will take Cl here as the stationary position, as Cl is a bigger atom as compared to the hydrogen. This is H1, H prime, this is H and H prime. So what will happen as the energy of this molecule increases from 0 to E1 level, the oscillation becomes more vigorous. Oscillation here means that the extension either this way or this way, the elongation will become increases. So we have seen any change in the bond length from its equilibrium position resulting in the change in the energy of that particular molecule. But one thing we should keep in mind, that when the oscillation, when there is an increase in the oscillation of the molecule, there will be no change in the vibrational frequency. There will be no change in the vibrational frequency of this diatomic molecule. So the molecules or the oscillation will change as the energy of this molecule changes, but the vibrational frequency remains same for any molecule. So if I further increase the energy of this molecule from 0 to E2, then the oscillation here means the compression and the elongation of the bond in this diatomic molecule will increase, but one thing remains same, that is the vibrational frequency. So it means any kind of a diatomic molecule, or I say any elastic bond, like we have yesterday taken the example of two atoms bonded by this spring, any kind of this kind of elastic bond, the molecule has some certain intrinsic, I can say, vibrational frequency. So the point here to be noted is that any elastic bond, the example is, we have taken the example of two atoms bonded by a spring. So that kind of, any kind of this kind of elastic bond has a certain intrinsic vibrational frequency. So each elastic bond, but the condition that bond should be elastic. So each elastic bond, just like a spring, this type of a molecule, in each at where these elastic bonds has a certain intrinsic vibrational frequency, and this vibrational frequency of each bond depends on the mass of the system and The one condition is that the intrinsic viscosity is depending on the mass of this system. It means in this case of a diatomic molecule, the intrinsic viscosity depends on M1 and M2. First condition. And the force constant. Second condition is our force constant. Force constant is what? This is K, and K is what? It is the measure of the strength of the bond. How much strong the bond are between these two atoms. So the intrinsic viscosity of any kind of elastic bond depends on two factors. One is the mass of the system. What is the mass of this total system means what is the total mass of the atoms including in that molecule. And second is the force constant. How much stronger the bond is between the two atoms. So we can say each elastic bond has a certain fixed amount of intrinsic viscosity, and that intrinsic viscosity is depending on the mass of the system and the force constant of that molecule. But your intrinsic vibrational frequency is independent of the amount of distortion. तो आपकी मॉलिक्यूल में कितना डिस्टॉर्शन प्रोड्यूस हो रहा है जब आप बॉन्ड को इलोंगेट करते हैं या कंप्रेस करते हैं, उस पे डिस्टॉर्शन पे आपकी मॉलिक्यूल की वाइब्रेशनल फ्रीक्वेंसी डिपेंड नहीं करेंगे. Only the factor on which your intrinsic vibrational frequency depend is the mass of the system and the force constant of that molecule. How now the term, this force constant, is a very important term, and it will, or I can say it will affect the vibrational frequency of any kind of bond. So if the force constant of the molecule is higher, then I can say then the well in your parabolic curve will be steep. So the structure of the parabolic curve will change depending upon the value of your K. Higher the value of K, that is the stronger is the bond between the two atoms, sharper will be the curve of this parabola. So this kind of curve we can got depending upon the value of your K. It means if the value of the K is higher, then the well of this kind of well is become very narrower, or I can say steeper. तो जितना आपका K का वैल्यू ज्यादा होगा उतना आपकी पैराबोला की वेल जो है बहुत स्टीप होंगे, और जितना आपका K का वैल्यू दैट इज द फोर्स कांस्टेंट का वैल्यू कम होंगे उतना आपकी वेल का जो है ये ब्रॉडर होते जाएंगे. सो वी कैन से द वैल्यू ऑफ K इंक्रीज इन दिस वे. So the force constant will increase in this way. Higher the force constant, narrower the value of your well in the parabola curve. So the force constant is a very important factor which determines the vibrational frequency of any diatomic molecule, but it is independent of the amount of distortion. Whether how much amount of by amount you can either stretch or compress your the bond of your diatomic molecules. So these two points we should keep in mind while doing the vibrational frequency, while discussing the vibrational energy levels on the frequency of a diatomic molecule. Now, classically, the oscillation frequency is simply given by, so classically, the oscillation frequency is given as your omega oscillation is equal to 1/2 pi under root K upon mu. So this is the equation of the oscillation frequency, that the oscillation frequency of your diatomic molecule, and it is given classically is equal to 1/2 pi under root K upon mu. Now, what is this mu? It is the reduced mass, which is equal to, if we have a diatomic molecule like this, that this is atom number 1, it having mass m, and this atom number 2 mass m2, then your reduced mass is equal to m1 m2 divided by m1 plus m2. So the mu is the reduced mass of your system, and the K is the force constant. That's why I have told you that the force constant is very important term. Now what we are seeing from this equation is that the oscillating frequency is the vibrational frequency is directly proportional to K, that is the force constant, and oscillation frequency is inversely proportional to the mass, that reduced mass. It means I can say higher the force constant, that is the stronger the force between these two atoms, higher will be the value of its oscillating frequency, and the reduced mass is inversely proportional. So I can say higher the mass of the system, mass of the atom of this molecule, lower will be the oscillating frequency, and lower will be the mass of this atom, higher will be the oscillating frequency. So this is the equation by which you can calculate the oscillating frequency, and the value of this, the unit of this oscillating frequency is in hertz. I can say it is the unit in the frequency term. Now, usually in spectroscopy, we have to convert this hertz, that is the frequency term, into wave number. So if I have to convert this frequency terms into wave number, then what will I do is simply I will put a bar on this, because we know that wave number are indicated by a bar. Then is equal to, just I have to divide this term with the velocity of light, that is c, and K and mu will remain constant, and now this equation will become in unit of centimeter inverse. So this is the equation of the oscillating frequency in terms of wave numbers. So the oscillation frequency in terms of wave number is equal to 1 upon 2 pi c under root K upon mu centimeter inverse. So this is the equation for the oscillating frequency. Now here also we have seen that the oscillating frequency is directly proportional to force constant and inversely proportional to a reduced mass of the system. Or in other words, we can say that the vibrational frequency increase with increase in the bond strength, and or we can say decreasing in the reduced mass of the system. So what will happen here is the frequency of the oscillation, when the frequency, this frequency of the oscillation matches with the frequency of the light, now you have this molecule, you have bombarded electromagnetic radiation on this atom. Then what will happen when the frequency, this much frequency will match the frequency of this electromagnetic radiation? What will happen? These two frequencies will resonate with one another, and it will absorb the electromagnetic radiation. Now these are the infrared radiation, and your molecule will undergoes transition from one energy level to another energy level. So again, here we can say that vibrational frequency, vibrational spectroscopy, because these two frequencies are resonating, we can say vibrational spectroscopy is also a form of resonance spectroscopy. Spectroscopy is also a form of resonance spectroscopy. Why we call this as resonance spectroscopy? Because until and unless the vibration, the oscillating frequency will not resonate with the frequency of this electromagnetic radiation, there will be no absorption of energy could take place, and the molecule will undergo transaction from one energy level to another energy level. That's why we can also call this is vibrational spectroscopy. We can also call it is also a form of resonance spectroscopy. Now let's come to the energy level, vibrational energy level. So your vibrational energy, what kind of energy values we can be allowed in case of vibrational spectroscopy is the vibrational energies, like any other form of molecular energies. That is where when we were discussing our rotational spectroscopy, we have said that the energy levels are quantized. So vibrational energy all are also quantized. Quantized means that only a certain fixed value of energy are allowed. Not all the form of energy are allowed. It means that the only that particular energy are allowed which will resonate with the frequency, with the oscillating frequency. Or we can say that a certain amount of energy is only allowed to undergo transaction from one level to another level. And the value of this energy system can be calculated by solving Schrodinger equation. Now we will not going into the into how we will solve this Schrodinger equation for vibrational diatomic molecule. It is a very time consuming step and it is not that much easy. Simply we say that for a we will write the equation for a simple harmonic oscillator, or we can say a diatomic molecule, any diatomic molecule oscillator. The solution of this Schrodinger equation turns to be this, turn out to be, जब श्रोडिंगर इक्वेशन को सॉल्व करेंगे आपको ये वाला इक्वेशन मिलेंगे एनर्जी के लिए कि vibrational energy, that is EV is equal to mu plus 1 by 2 half of H omega oscillation. So this is the frequency and this is in terms of your hertz. Not hertz, this is the energy, so it is in terms of joule. Now when you solve the Schrodinger equation for a simple harmonic oscillator or for a diatomic molecule, you will get an equation of this type where vibrational energy is equal to mu plus 1 by 2 H omega oscillation. This mu is nothing, just like what we have J in case of rotational spectroscopy, that was rotational quantum number. This mu is your vibrational quantum number, and the value of this mu will be from 0, 1, 2, 3, 4, 4, 5, 6, and so on. So it can have any integer value starting from 0. So this mu is our vibrational quantum number, just as we have J in case of rotational spectroscopy. And this can have numbers starting from 0 to any number. So what we are seeing here is that the unit of this energy is in joules. So what we have to do is we have to convert it into the spectroscopic unit that is in our wave number unit. The wave number unit is what? Centimeter inverse. Now we have to convert joule into wave number unit. For that, what we usually do is, let's I have to take epsilon V is equal to, I have to divide this EV with our HC. I have to divide EV our HC, and when you will do this, you will get equation mu plus 1 by 2 omega oscillation. Here H and this H will cancel each other, and we know that 1 upon C is equal to mu upon 1 upon lambda, that is wave number unit, is equal to mu upon C, that is oscillation divided by C. So now this is the form of energy equation in spectroscopic unit, that is our centimeter inverse. Centimeter inverse. Now this is the actual equation for energy of a simple harmonic oscillator, or I can say energy equation for a diatomic molecule. For a diatomic molecule. So this equation is very important, and this should be kept in your mind while solving the, I can say, while solving the energy of your diatomic molecule, or I can say simple harmonic oscillator. So these are the only energies allowed to sample a harmonic oscillator or vibrational energy levels. Now let's draw some energy levels by using this equation. So now let's draw vibrational energy levels. What kind of energy levels we can get by using this equation? So we know that the energy equation we have V epsilon V is equal to mu plus 1 by 2 omega oscillation bar. Okay, so this is our equation in terms of wave number. Now we know that the value of V can be 0, 1, 2, 3, 4, 5, 6, and so on. Now let's substitute the value of V in this equation. So EV0, E0 is equal to, when I put 0 in place of V, this will become, what we have is 1 by 2 omega oscillation bar. So the first point is, when V is equal to 0, the value of your energy is half of omega bar oscillation. This is very important, and this is also known as 0 point energy level. What is the difference between our rotational spectroscopy and the vibrational spectroscopy is that in case of rotational spectroscopy, our lowest energy level was there. We have got that the value of R0 is equal to 0. However, in case of vibrational energy levels, E0 is equal to 1 by 2 omega oscillation bar. It means that the bonds are never at rest. What is the significance of this 0 point energy is, these are indicating that bonds are never at rest. आपका bond जो है वो कभी भी rest position पे नहीं रहता है. It means the bonds always vibrate with some energy, and that energy is equal to 1 by 2 omega bar, omega oscillation bar. So the bond, even at the rest position, also will be vibrating with a frequency equal to half of omega oscillation bar. So this is very important. E0, also known as 0 point energy level. When I substitute E is equal to V is equal to 1, then E1 will be 1 plus 1 by 2 omega oscillation bar. So what will be 2, 1, 2 plus 3. So I have a value 3 by 2 omega oscillation bar. Likewise, if I will put V is equal to 2, then 2 plus 1 by 2 omega oscillation bar. What will I get here is 2 to 4 plus 1, that is 5 by 2 omega oscillation bar. So next energy level be V is equal to 3. 3 plus 1 by 2 omega oscillation bar. 3 to 6, 6, 7 by 2 omega oscillation bar. So what I got here is the difference between 2 in each energy level. 1 by 2, 3 by 2, 5 by 2, and 7 by 2. So I can draw an energy level diagram here. Is now this is your energy axis and this is your internuclear distance. Internuclear distance, and this is our energy, kilojoule per mole. Now, before drawing the energy level, what we will first do here is what we will just find out is there what are the difference among between the energy levels or the all the energy levels, the distance between the energy levels are same or not. So again here we have to apply the selection rule. So before going to selection rule, let me discuss some another important point regarding this 0 point energy level is that the prediction of this 0 point energy level is the basic difference between your classical approach and classical approach and your wave mechanical approach. Wave mechanical approach. So classical approach has no objection if the value of energy is equal to 0. But the wave mechanics says that the vibration of any kind of molecule or bond will never be 0, and it always vibrate to some extent with some energy that is equal to 1/2 omega oscillation bar. So this is the difference between classical approach and wave mechanical approach. Further, I can say the selection rule for this vibrational spectroscopy is the important the gross. There is two selection rule. The first selection rule I can say that is gross selection rule. Gross selection rule is that mu is should not be equal to 0, d mu upon dx. That is, there should be a change in the dipole moment for a molecule to show to show that it is vibrationally active. So this is the gross selection rule. The specific selection rule is that delta mu is equal to plus minus 1. So the transaction should only take place from one energy level to another energy level. Now I will draw the energy level diagram. So the energy level diagram for a vibrational energy level diagram for a diatomic molecule will be like this. This is my parabola, and these are the vibrational energy levels. So this is equal to V is equal to mu is equal to 0, mu is equal to 1, mu is equal to 2, mu is equal to 3, mu is equal to 4, mu is equal to 5, and so on. And the energy value of energy is for mu is equal to 0, it is half of omega oscillation bar. Then this is 3/2 omega oscillation bar. Then this is 5/2 omega oscillation bar. There is the value of the energy 7/2 omega oscillation bar. Then it 9/2 omega oscillation bar, then 11/2 omega oscillation bar. So these are the value of the corresponding energy levels, and these are the vibrational energy levels. So according to the selection rule, during the transaction, delta V should be changed in only plus minus 1. It means the transaction can occur from this level to this. It can only from this level to this, and in the reverse order, and this is to this, and then from this level to this level, from this level to this level, and also in the reverse order from this to this, this to this, this to this, this to this, and from this level to the next lower level. So the change in the value should be only plus minus 1. So if I will apply the selection rule and will find out whether the difference between these two energy levels are same or different. In case of our rotational spectroscopy, the energy levels we drawn is like this. The gap between first energy level is higher, then it then it increases and increases and increases and so on. So इस तरह हमारा एनर्जी लेवल्स के बीच में गैप चेंज हो रहे थे, लेकिन यहाँ पे हमने ड्रॉ किया सारा एनर्जी लेवल्स क्या है, हम हमारे पास बराबर है। तो क्या ये बराबर है, क्या हम सही ड्रॉ कर रहे हैं, इसको अगर हम देखेंगे तो क्या होगा, अप्लाइंग selection rule, if I have to find the difference between two energy level, for example, if I have to find E V plus 1 minus E V is equal to 0, what I have the value of E V plus 1 is 3/2 omega oscillation bar, and for E0 it is 1/2 omega oscillation bar. What will be the difference between these two? Two are same. 3 minus 1, 2/2 omega oscillation bar. So this will cancel. I will get omega oscillation bar. So the difference between our first higher energy level and the ground energy levels, what we got is omega oscillation bar. The value is omega oscillation bar. Similarly, if I can take the difference between V plus 2 minus EV is equal to 2 EV is equal to 1, then the difference will be EV is equal to 2. The value is 5/2 omega oscillation bar, and for EV is equal to 1 is 3/2 omega oscillation bar. So the difference will be 5 minus 3 is 2/2 omega oscillation bar. So 2 and 2 cancel again. The value is omega oscillation bar. Similarly, if we see the difference between EV is equal to 3 minus EV is equal to 2, the value will be 7/2 omega oscillation bar minus 5/2 omega oscillation bar. What will be the difference is again 2/2 omega oscillation bar, 2 will 2 cancel, and it is omega oscillation bar. So what I am getting here is that the spacing between any two transaction levels, whether it is just what we are drawing here is V0, V1, V2, V3, and the spacing between these energy levels are equal. Every energy levels are equally spaced. इन कंट्रास्ट टू आवर रोटेशनल स्पेक्ट्रोस्कोपी में हमने देखा कि एनर्जी लेवल्स क्या थे, slowly the gap between the energy levels were increasing as we increase the value of the rotational quantum number r j. However, there the spacing between any energy level is remaining constant, and the spacing between two energy level is equal to the oscillating frequency, that is omega oscillation bar. So what will happen here is that again the difference among the energy levels, or I can say the energy levels, are equally spaced. So transaction between any neighboring state, whether it is from V0 to V1, V1 to V2, or V2 to V3, give rise to same energy change. So in the spectrum I will get only one line. So the spectrum will be like this, that if this is the spectrum, so I will get only one either absorption or emission band at omega oscillation bar. So this is what are the difference between your vibrational and rotational energy levels, and what kind of energy levels we can get for vibrational energy levels. And again, the absorption will only occur when these oscillating frequency will resonate with the frequency of our electromagnetic radiation. That is, in case of vibration, we are using infrared light. So again, when these two frequencies will resonate with one another, the absorption will take place, and your molecule will undergo transition from one energy levels to another energy level. So again, the important point here is that all the energy levels are equally spaced. We can get the energy for any transaction of any between any energy levels. We can get same energy. So we can have this omega oscillation per frequency. So that's all about our vibrational energy levels of a diatomic molecule or simple harmonic oscillator. So thank you for today.